Assalamualaikum, very good morning, dear students. So today I'm going to continue our next topic for our computer architecture and communication class under chapter 6, which is under interfacing and communication. So before we start our class, okay, I would like to give my thanks for you guys to you guys for your commitment in completing all the chapters and then continue with me up until the end of the semester. So hopefully we will finish. Actually, it's around two more topics left up until chapter 8. So this is the third last topic that we have here. So without further ado, let's start our topic now. So okay, so in this chapter, we are covering under interfacing of communication means how data travels inside your computer, especially between the peripherals, the processors within your computer. So firstly, okay, I would like to start with the peripherals that we have first. So these are the examples of our peripherals that we have in our computer. So this one, okay, you are familiar with it, which is the game controller, keyboard, speakers. This one is for your CD, this one is for your videotape, printer, and also for mouse. So all of this require communication between the computer and the outside world. Okay, so you cannot use them without a computer, and they are not working without any interaction from outside world. So these are what we call input and output. So what are input device? So basically input device is those who take data, who takes information from the outside world and converts them into a digital data. So example is that your keyboard takes the information from you pressing the keyboard and turns it into a digital data. So other than that, we have this mouse, and then we have this game controller. All of them plays the same information, play the same role as an input device. So CD, for example, it can behave both as an input and output device as well. So next we have the output device. So the most common output device in your computer's setup is usually the monitor, and sometimes you might have a printer with you. Okay, so printer is count as an output device as well. If it's include a scanner, so scanner is an input device. So output device is where you have the digital signals and you want to convert them into uh, uh, physical information, like for example screen, or for example audio from your speaker. Okay, so some of them can behave as both, okay, for input and output device. Example is your network, okay, network devices. So this one example of a network modem. So previously we have this one. This one is in late 1990s that consists of dial-up communication within this modem. And here is an example of a network card for your PC. Okay, previously, 20 years ago, 30 years ago, some of computers do not have the network card included inside the PC. So you have to include an expansion board to include the network card as well. So some of the device, they behave as both, like for example, input and output. Okay, example of input and output are the touchscreen, okay, and then the pen drive, CD, DVD, they can be input and output as well. So this is the difference between the input and output device for your PC. So within the input and output, usually we have a wide variety of peripherals, and they are delivering different amount of data, okay, and then they have different speeds, and they are usually presented in a different format. So example, imaging, you have a different format than audio. So we need an IO module for us to supervise all this information coming in into the PC. If not, our CPU will be burdened of all this information coming in. So the IO module, basically they are not connected directly to the CPU. So the devices, they usually connect to this I/O module first, and I/O module will control what kind of information is coming in into the computer. And I/O module, they are connected to the CPU using 3 lines of the system bus. They have the address line, data lines, and the control lines. So address line includes address of any kind of location or within the PC. Data means data involved, and control lines means either it's for read or write. So I/O modules, basically they act as interface for the external device to CPU and memory via the system bus, and they interface to one or more external devices by a tailored link. So this is example of the I/O module architecture. They are connected into the address line, data lines, and control lines, and the bottom one is where the links to the peripheral device is developed. So okay, so why can't we connect the peripheral directly to the CPU and the buses without the I/O module? Okay, so one of the reason is that we have different kind of peripherals, so they have different functions, thus require different control logic to gain the information. So some of them also have a different data transfer rate. So some of them, they are very fast, and some of them, they are very slow for the CPU to process. So this one create a problems where there are a lot of peripherals for you to attach to the PC, and you have problems in timing distribution of those data. And those data also, they have different format and different word length depending of what kind of information they bring. So some of the bigger data information that coming into your PC comes from your camera. Okay, the less data coming to your PC, like for example from your keyboard. Keyboard doesn't have much data information to come in into your PC because they're just a button. But camera, they carry images, so they have a huge data type, huge size, a data type with huge size for your CPU to process. So that's why we have, for each different peripherals, we have this device interface that operated by the device driver. So depending on what kind of device, we have different types of interfaces within your PC. So all these interfaces, they are connected into your I/O module, and I/O module will control the distribution of the information from your devices into the processor. So basically, if you look at memory, they have what we call a memory addresses and also data. So memory address represent where in the location within the memory hardware your data is located in. But for interface device, okay, I/O module will control address from which device the data is coming in from or coming out to, and based on these addresses, okay, it will communicate with the processor. So example of external device, okay, we have 3 types of external device basically that we have. So the first one is the human readable, the second one is the machine readable, the third one is for the communication device. So human readable device example is your monitor, okay, and also your speaker, or even we count as your sound also as human readable, even though you hear it, okay, because you can read the data by your ear. Okay, so we call it as a human readable as well. Next one, we have what we call the machine readable. So machine readable suitable for communicating with equipment. Like for example, we have a CD, your pen drives, okay, your a lot of previously we have magnetic discs, tape systems, okay, so all of them are machine readable, means that the external devices, they only can be used with a PC. Okay, you cannot use it independently than the PC. So this is what we have, machine readable. And the final one is for communication device. So communication device is for communication between one device to another. So this is basically what we call a modem, your network interface controller, okay, your network devices, switch, everything, and sometimes we include sensors and actuators as well. So for all those device, external peripherals, so we call it. So the basic architecture of those peripherals is as displayed here. Okay, they must have 3 things within their component. They have a transducer, they have a buffer, and they have a control logic. So transducer is the one responsible of getting the information from the environment. So anything happening in the environment, they will convert them into a data. And then we have a buffer to hold all the data, and we have the control logic that depending on what kind of signal coming into the device, okay, it will send the data or receive the data. So if the control signal want to read the device, okay, means the CPU want to read the device, control logic will give a response, either it is ready or not ready, okay, to give the data. And once it's ready, it will transfer all the information stored in the buffer to the CPU. So this is basically the architecture for all the external devices in the world. So the function of the I/O module, basically they are for 5 things. Okay, so first one is for control and timing, means that they are used to coordinate the flow of the traffic between internal resources and external resources. And also they are for processor communication, means that everything wants to communicate with the processor, either for the purpose of read, write, okay, exchange data, status reporting, okay, and also address recognition. They will need to go through the I/O module first. So this one is like a guard before the boss, okay. And then we have the device communication. So the device communication, okay, this is for you to communicate, for the PC to communicate with the external device. And then for data buffering, so means that it try to temporarily hold data between the being transferred between the I/O module and the external device. So sometimes data processed by the CPU is a lot. So when you want to transfer them to the outside device, it takes time because the device is occupied with something or maybe quite slow. So the buffer, okay, the buffer of those data is located, sometimes it's located into the device, but okay, there are limited space in the device, so most of them, they are located inside the I/O module. And finally, the final function is for error detection. So this one will detect error and report error to the processor regarding malfunction device, okay, problem with any external device that attached to the PC. So for control and timing, okay, so this is the step for control and timing. Okay, like for example, step 1, let's take a look at step 1. The processor interrogates the I/O module to check the status of the attached device. The I/O module then, okay, returns the device status. If the device is operational and ready to transmit, the processor will request the transfer of data by means of a command to the I/O module. Okay, they will tell I/O module get the data to the processor. Okay, the I/O module obtains a unit of data, okay, from the external device, and then the data transferred from the I/O module to the processor. So everything when the CPU wants the data from the device, okay, they will send the request first, basically to the I/O module. I/O module will control whether they can get the data or not. Okay, so you will check whether the device is ready for the CPU to get the data or not. So we don't want the device to give up, to give to the CPU faulty data, everything, not unfinished data. So they make sure that the devices provide adequate data that the CPU needs for the CPU to process at the time the CPU needs. Okay. So for processor communication, okay, they involve 4 things. Okay, basically the first one is commands from the processor, and then we have the data, and then we have the status reporting, and also we have the address recognition. So basically for CPU communication, so when the I/O module communicate with the CPU, okay, they just communicate with exchange of command, whether it's either for the CPU want to read or write the data, okay, and then the I/O module will reply either busy or ready, okay. And other than that is the data and also the address of the components that within the I/O module. So when the CPU asks for control, basically just send I want to read, and then the I/O module send back to the CPU, okay, I want to, I am busy, okay, I'm not ready, I'm busy, or I am ready, you can get it from me. So when they say that they are ready, data will be given, and also address recognition will be given to the CPU. Okay, And then we have the status reporting, okay, whether the device is slow, which means it's busy, or is ready when it finish processing. And finally, the address recognition, okay, it's a kind of setup as a block of one or more unique address to itself to allow referencing. So it means that when the CPU wants to send information to a device, it need to refer which device you want to send to. So basically, the I/O module will determine what kind of address this device have. Like for example, if you are familiar with your Windows, you might notice that we have what we call a COM port inside your PC. So there are a lot of port. So these are the port example of addressing that you have for each of your device. So next we have, okay, we have for device communication. Okay, so here specific to each device, each I/O module able to establish communication. Communication involve command, status, and data. So as mentioned before, using these three lines. And then we have data buffering. So in case they are slow, they will hold the data first, okay, before either CPU or the device can get the data. And then for error detection, okay, they will detect malfunction of the device. Like for example, in case of your printer, you have paper jam, okay, and then in case of your hard drive, you have bad disk track. And then you have for data errors, which the I/O module will issue parity checking at the device level in case of your faulty external devices. So these devices, they are connected to the I/O module as in this architecture here. Okay, so all these three lines, they are connected to the I/O module, these left three lines. Oh, sorry, this right three lines. So this one, okay, this module for the peripheral module here, they are representing one of this external device interface logic. So they are representing into connected to one of this. Okay, so here data coming in into either any interface logic here. Okay, this is one example of one interface logic, and from here they will go towards the I/O logic. So I/O logic, the purpose of the I/O logic is for it to allow data coming in or coming out of the I/O module. So we depend on the control lines provided by the CPU. Okay, I/O logic will give out the address lines of what kind of information, what kind of address each of these interfaces have. And from here, you have a control register that provide the status of the device, or even sometimes it provide the data directly when everything works fine and you want to transfer the data. Okay, data is coming out from the data lines. Okay. So basically that is the whole story of those I/O module processors. And then we have the instruction. Okay, so basically when the processor issues something to the I/O module, okay, they will issue according to these two syntax, which is the address and the I/O command. So address mean the particular device that is connected to the PC, the location of the device basically. And then the I/O command is whether to control, test, read, and write. Okay, so all of this basically normally they have only read and write. So and then when they want to read, okay, the I/O module will reply busy or not. So these are the common syntax that we have when the CPU issue a command towards the I/O module. So there are two types of addressing. We have the memory map I/O and also the isolated I/O. So the memory map I/O basically single address space for memory and I/O device. Okay, processor treat the status and data register of the I/O module as a memory location. So it means that I/O module behave exactly like another memory. So they use the same instruction to access both memory and I/O module. And for example of that, so for example in this case of 10 address line, you have 2 power of 10 memory location plus I/O address that can be supported. So what is a memory map I/O? Okay, so memory map I/O basically, instead of having special methods for accessing the values to be read or written, you can just get them from memory or put them into a memory. The device is connected directly to certain main memory location, and two status of information, okay, whether it's coming in or coming out from the device, whether it's a status or it's a value for read or write. Okay, so why do they use the memory map IO? So memory map IO makes the programming simpler because IO is a part of the memory as well. So it doesn't need to change much to differentiate between those two components. So they don't have special commands to access the IO device. So however, it takes some of the memory location. If you compare it with the size of the main memory, current memory even better, there are very few. So it's not many because you don't have a lot of device attached to your computer at one time. Next, we have tools that we have what we call isolated I/O. So isolated I/O is where address space of memory and I/O is isolated. So the command line inform whether address refer to the memory location or an I/O device. So example, they can be, in case there are 10 address line, it can be 2 power of 10 memory location, or it can be 2 power of 10 I/O address. So it can be either one. It cannot be combined together. So differences between this kind of memory map, this kind of mapping I/O. For isolated I/O, they use separate memory space. Memory map I/O, they use the same memory location within the main memory. Isolated I/O, okay, they limit instruction that can be used. Those are like, for example, in this case, in, out, ins, and outs. And then for memory map I/O, we have any instruction which references to memory can be used, which means that there are more universal instruction available for your devices. The addresses for isolated I/O devices are called ports, and memory map I/O devices are treated as memory location on the memory map. And finally, okay, IORC and IOWC signals expand the circuitry. However, for memory map I/O, IORC and IOWC signals has no functions in this case which reduce the circuitry. Okay, so up until now is the first part of this chapter. So I'll continue again in our next chapter later on. Thank you for staying with me. Hopefully you stay tuned for our next video that maybe I will post in the next 1 or 2 days later. So thank you for your support. Stay safe, stay healthy. Bye bye.